Okay, hello, everybody there? Okay, let's give this one more minute. Okay, give me one more second here. Hello? Let me turn that back. Okay, let's I guess get started. First of all, any questions about anything logistical or technical? Who is still looking for a homework partner? I see one. Do I see more than one? If somebody else raises their hand, I see one here, I see one there. Look at each other. You guys see each other? Make contact, you're now partners, okay? And any questions about that? Yes? Okay, the question has to do with balanced binary tree data structures. What I'd like to do today is to quickly finish up talking about balanced binary trees. Just quickly what they, complete the story. We're not going to go into as much detail as I might like, okay? Again, balanced binary tree data structures are amazingly beautiful data structures. You've heard the poem, okay, again, it's Valentine's Day. You should recite poetry. I think that I shall never see a thing as lovely as a tree, right? And recite that to the one you love and see how far it gets you. But we are going to talk here about balanced binary trees a little bit just to summarize why we care about them, because this is what is important, okay? We have talked about, from last class, we went through and looked at all the main dictionary operations. Insert, delete, search, find the min, find the max, find the predecessor, find the successor. All of these, when implemented on as a binary tree, take time proportional to the height of the tree. Okay? Okay? Proportional to the height of the tree. Okay? And we're going to stick n nodes in our tree. Our dream is the best tree we could possibly get with n nodes in it would be perfectly balanced. If it's going to have room for n nodes, the number of nodes we get in each level, okay, is going to be, okay, the homework's for the days we started. So, okay, we don't want to collect that now. Okay, so balanced binary search tree. We've got n nodes. If we think about our binary tree, there are, with one level, we can have one node. With two levels, let's try this again. With one level, we can have one node. With two levels, we can have three nodes. With three levels, we can have 7 nodes. Does everybody see this? With 4 levels, we can have 15 nodes. The number of nodes potentially doubles with the height. Does everybody see that? That says that if you want to stick n things in a binary tree, if everything needs a node, it's going to have height at least log n. Okay? If we have a tree of height log n, then all of these operations would be order log n. Okay? But if we get right now, implementing insert and delete the way that we did last time, we have no control of the order of operations that we're asked to do. Okay? And because of that, we could end up with a horribly lopsided tree. Does everybody agree with that? Any questions about that? Our dream would be that the tree be log n in height. Okay? But because right now the way we've implemented it, we're at the mercy of the order of insertions, we can't quite make that guarantee. Again, if you give me things to insert in a pathological order, in a sorted order, okay, then again the tree is going to turn into a long skinny twig. And it will be of height n instead of log n. Any questions about that? That's important to see. Now, there are a couple of ways out of this problem. One is to argue that, in fact, the order of insertions, if you give me the keys, insert them in a random order, not a pathological order, the tree is probably going to be pretty balanced. And let me try to argue a little bit like that. If I have a perfectly balanced tree with n things in it, okay? Here's a perfectly balanced tree with it, okay? What is going to be, if they were inserted in the order of the number 1, 2, 3, this is the in-order traversal I'm doing, right? 9, okay. You see what I'm doing? The root is going to have what number if we have a perfectly balanced tree on the keys 1 through n? What is the number of the root going to be? Yeah? About n over 2. Does everybody see that? That it's in the middle, right? What is our dream of what the first insertion into a binary search tree would be? Okay? If we were inserting ultimately numbers 1 through n, we can't control what they're going to do, right? But what would we want them to do as their first insertion, yeah? The median is the root, right? If you pick the numbers from 1 to n at random, what is the average value? Okay? It's going to be n over 2, which is kind of what we want, okay? So it's a little bit hand-waving what I just said. But what I want to argue is that if you pick the numbers from 1 that came in random order and inserted it, the root value is more likely to be sort of near the middle than one of the ends. And that's what we would kind of like to have happen. And if you're repeatedly picking the order of these things in a randomly, you randomly permute the numbers from 1 to n, insert them in a tree, in fact, the order of the tree is going to be balanced. It is going to be actually theta of log n. Okay? Now, the question is, are people going to do things in a random order? Okay? In general, which do we think is more likely when you have a tree data structure? That someone is going to do random orders of insertions, or that they insert things that happen to be in sorted order, in the order that they were sorted? Okay? I don't know if anybody can answer that, but I think that you will agree that there is a certain chance people are going to insert things in sorted order. Okay? You can imagine that somebody pre-sorted the file. Like, let's say I wanted to build a binary search tree on the class roster. How would I do that? I'd probably take a file of the class roster from something which may have already been sorted, right? So there's a real risk. Although on average, if you give me random order of things, my tree will be nice and well behaved. In practice, this insertion order, this linear time thing is a real danger, okay? Because probably sorted order is the most likely single order in practice that you will get these things. Any questions about that? Does that make clear? So the other thing to note is, so we could do one of two things. We could hope that our tree is going to, inserts will be random, and then we will have log n stuff, okay? The other possibility is we do some extra work whenever we have an insertion or a deletion to try to keep the tree balanced, okay? So the argument is going to be that if you have a tree that is right now sufficiently balanced, the height is order log n, if you insert something into it, that thing is now going to get inserted at the leaf. It's now the deepest thing. It might cause an imbalance, right? It might be more than log n or 2 log n or some constant times log n deep. If so, you've got to do something to fix the tree to make it more balanced, okay? And when people talk about balanced binary search tree data structures, the trick is that when you do an insertion deep in the tree, you've got to do something to fix it. Does everybody get that idea? Okay? And, you know, so when you, again, I'm not going to go through the details of how balanced binary search tree operations work or don't work. But it should be, I guess, the key ideas are the following. Okay? First of all, if I insert a node okay, and it's deep, that it causes the tree to no longer be balanced. This node is the place that has to be fixed up. That should be clear, right? The tree was balanced before, and I insert you at the leaf. There is a place where the problem is now localized, right? And so if it's localized, maybe there's a way to fix it locally. Does that make sense? And how would you fix it? There was some operation that in a data structures class you learned called a rotation that said that if we have a tree node like this, okay, where you've got a root node, here you've got, let's just call this thing 1, 2, 2, and 3, there is an analogous local tree which has the same values in it, which will still be a binary search tree, where you will have shifted things around. Okay, let's see if I can figure this thing out. If I may, look at this tree. If I label this node A and this node B, corresponding to what I had there, this branch 1 was the stuff that is less than A and B, right? Does everybody agree with that? Where in my new tree must number 1 be? To the left. Does everybody see that if this is 1, that thing's got to be there, right? And this thing 3 was bigger than B, which is bigger than A. Where does 3 have to be? Over here. Does everybody see that? Now number 2, okay, is in middle. This binary search tree, again, it comes from a root. This comes from someplace, okay, is functionally equivalent to this one. It's a local change. It's still a binary search tree. But if this part was very deep, let's say that the trouble was over here, this was the deepest thing. Note that when you do this rotation, it's been lifted up 1 level. So by applying these rotation transformations, you can make the tree more balanced, okay, if you apply the right moves at the right place, okay? How many people are sort of with me now? Okay, any questions about it? Okay? So there are these very, very beautiful data structures that exist. Things like AVL, let's get rid of this off of here. Clear ink. Okay? There are these, when we talk about balanced binary trees, we are talking about a implementation where the tree is guaranteed to be order log n in height, if it's got n nodes in it. Not exactly log n, because it turns out that doesn't give you enough freedom to make fast updates. But here's a question for you. If you have a tree of height 2 log n, how many nodes might possibly be in a tree of height 2 log n? 2 times log n. Okay, yeah? N squared. Does everybody see that? Probably not. Okay? How do you tell this thing? Well, if we're doubling something 2 to the log n times, what is the number of nodes that might be in there? 2 to the 2 log n. Right? And what is 2 to the 2 log n? That is equal to, wait, what is it? 2 to the log n squared. Say 2 to the log n squared. Wait. Okay, the way I think of 2 to the log n squared, this is the same as, okay, what I want to say is that the 2 to the log n, what's 2 to the log n? Okay, 2 to the log n is n. So by solving this part of the thing, it comes out to be n squared. Okay, that's where the n squared comes from. Okay, if you simplify 2 to the 2 log n, you get 2 to the log n is n to the 2 is n squared. Okay, what does that matter? A tree of height 2 to the log n has room for n squared nodes. If we only want to put n nodes in there, there's lots and lots of trees that will do that. Okay, and there's a lot of room if you want to put n nodes into a tree of height 2 log n. Okay, so it turns out that with that flexibility, if you apply these rotations in the right way, everything can be fixed up nicely on an insertion. Okay, any questions about that? That's maybe a little too hand-wavy to understand, but the punchline is that there are ways to fix up trees so that all these operations can be guaranteed to take log n time. The tree is going to be of height at most twice n, log n, okay, and therefore all these operations will be order log n. Any questions about it? So again, there are these really beautiful data structures. In your class, you may have learned about data structures, about AVL trees, or red-black trees, or 2-3 trees, or B trees, or splay trees. They all differ a little bit in how they fix up the problem, okay, when something is inserted too deeply in the tree to make it unbalanced. But bottom line, you can assume some smart person has figured this out. You can assume some decent programmer has implemented it. And that there now is a data structure, a balanced search tree data structure implementation that will, for every insert, delete, min, max, successor, predecessor operation, will guarantee it will take log n time for n things. Any questions about that? Any questions about balanced binary trees, why they're good things, how they work on this level, anything like that? Okay, so now let's assume that these trees exist. If so, then, actually, let's see if I can do this. Bunk. Oh, good. That's it. Let's get to the problem of the day. What is the problem of the day today? Okay, I like to check these things quickly. It says one about, okay, here's what I thought it was. Okay, so let's look what the problem of the day is. It says that you are given the task of reading in n numbers and sorting them. Okay? You have access to a balanced binary balanced dictionary data structure, okay, which supports all of the basic operations we talked about: insert, delete, min, max, successor, predecessor. All of these can be done in log n time, and you assume that you've got, it's been implemented, okay? Now the question is, explain how you can use this to sort efficiently, okay? So how can we use a balanced binary search tree to sort in n log n time, okay, using only the operations minimum, successor, insert, and search? Any ideas? Okay. Yes.
First start with the minimum element. That will take log n time.
Well, start with the minimum element. Tells me with what? Okay, so let's think what this means now. Now I don't understand it at all. Okay? I am given in the task of reading in n numbers, okay, and printing them out in sorted order. Right? So all I am given is an array of n numbers, presumably. Now what do I do with it? So first of all, what do I need to do? You're telling me something like for I equals 1 to n, insert into my tree, okay, the element a sub I. That's what I'm hearing you say, right? What is this going to do? To get data into my tree, how do I get it into my tree? The only way to get data into my tree is to insert it. Does everybody agree with that? So how much time does it take to take my array of numbers and put it into a tree? Yeah? N log n. And why is it n log n? Because I am doing n things, each of which takes order log n time. Does everybody agree with this? Now, after n log n time, I have gotten nowhere except putting it in the tree. Now what do I do? Yeah? Now you're going to say to me that m is equal to the min of the tree, right? Now I've got that one, right? And now what are you going to do?
Now put that into the first element of the array.
Okay, so what you're really now saying, I think, is something like print m. Now, once you've done that, print m, because that's the first number in sorted order, right? And now what are you going to be doing? M is equal to successor, right, of m, right? Take what was the minimum element and find its successor. What is the successor of the minimum element? The second element in logical order, right? Does everybody see that? And now if I repeat this thing, maybe I'm going to want to do this thing something like repeat. You know, I might want to put the print here. Again, my code is lousy, but I'm going to say for I equals 1 to n, print m, and find the successor of it. Does everybody see what I'm doing here? I am now going to make, according to this thing, n calls to the successor, right? What is the complexity? How many people see how this algorithm is working? How many people don't see it? A question like, I don't see it is a good question. Any questions? Okay. Any questions? So what's the complexity of this thing? To build the tree took n log n time. To find the minimum element took how much time? Log n. And now I'm going to do, how much time is it going to take to find each successor? Log n. And how many times am I going to find successors? N minus 1, or n, you know, to my wound way of thinking. How much time do I spend printing things out? Well, or one time to print out each item. The total printing cost is only order n, right? But what I'm hearing is I'm going to spend n log n to insert and n log n to trace through each one of these things in a total of 2n log n, or order n log n. I have sorted. Any questions about this? This is important. This shows why data structures are an amazing thing and balanced binary search trees are an amazing thing. Just doing this, I have found the fast way to sort. Yes? Okay, you're saying I'm not using search. In this case, I am not using search, okay? But it is there if I wanted to, but I'm not going to, right? I'm using my data structure to solve the problem I care about, which is sorting. And in this case, I didn't need search. Okay? I could have at any point searched for something, but I didn't need to, right? It's like you're a Google user. I'm a Gmail user, okay? At any instance, I'm using Gmail. I could go to Google and also do search, right? But if all I want to do is to write Gmail, I don't need to do that, right? And in this case, I didn't need the search. Oh, I see. What you're saying is I'm allowed to use search. In this case, I didn't need to use search. Okay? That's 100% right. Any questions here? Okay? Very good. Let's look at another example. Another way we can come up with an n log n sort, just using our dictionary. Suppose we are only allowed to use minimum, insert, delete, and search. Okay? How can we now sort using these operations? Yes? So first thing I'm going to do is for I equals 1 to n, insert into the tree a sub I, right? And that's going to take a total of how long to build the tree? N log n, right? Now that I have the tree, what am I going to do? Find the minimum, okay, min, okay, and we're going to say find the min, so m is equal to the minimum element, okay, and now what am I going to do? Print m, and then what am I going to do? Delete m. Does everybody see that? Right? And then what am I going to do? So long as while it's not null, okay, or if I know there's n things in my tree, if I happen to know there's n things in my tree, I'll just do it as a loop, for I equals 1 to n. Does everybody see that? So he's going to do it by finding the min in the tree, deleting it, and then finding the next min. Does everybody see that? What's the time complexity of this? How much time did it take to find the min? It took log n. How much time did it take to print m? 1. How much time did it take to delete the min? Log n. What is log n plus 1 plus log n? Log n. And how many times am I going to do this? N. And what is n log n plus n log n? N log n. Does everybody see this is another way to sort in n log n time once you have the magic powers of the balanced binary search tree data structure? Any questions about that? Okay. Again, the way I think about data structures, man makes progress by the number of things they can do without thinking. I do not have to think about this complicated rotation stuff and how they are implementing this balanced binary search tree anymore. That is detail under the hood. Mr. A, V, and L of the AVL trees figured that out. Okay? They have bequeathed me a balanced binary search tree data structure. Okay? So I know this can be done, and once I know what it's done, I can use it to design algorithms using the performance guarantees on each operation. Any questions? Let's look at the last one. Here I'm only allowed 2 operations. One is insert, and the other is in-order traversal. Okay? That means to go through, perform an in-order traversal. How would I now do sorting in this way with these 2 operations? Any ideas? Yes? So 4, I equals 1 to n, right? Insert into the tree T, okay, A sub I, right? And now what am I going to do? So now when I have a tree, again, we didn't really mention this I did on a slide. I don't think I talked about it. But there is this notion that when you do an in-order traversal, where you start at the root and you say visit everything on the left, print out the name of the root, then visit everything on the right, recursively. That was what we meant by an in-order traversal. How many people saw in-order traversals in their data structures class? How many people did not see in-order traversals in data structures class? Okay, a couple, okay, but relatively few. Look, if you didn't see it, look at my slide on how the in-order traversal works, okay? But what's the time complexity of an in-order traversal on n nodes? This is a more interesting question. Does anybody know? How much time does it take to do an in-order traversal? So you're saying something about log n and stuff. Actually, in-order traversals turn out to be linear in the size of the tree. Let's think, maybe it's worth talking about here. Let's try clearing it out. What is an in-order traversal? Clear. Okay, so let's take a tree and make it here is a tree. Let's say that this is what I'm going to do. What is the in-order status of the tree? Those are the nodes in the order that they would appear, right? In an in-order tree, in a binary search tree. What happens in an in-order, in doing an in-order traversal of a tree? The basic algorithm, if we could even write that out, that to do a traversal of a tree T is to traverse T dot left, the left sub-branch of it, right? Print the root ID, the root of the tree, right? And then traverse T dot right, the right side of the tree. Okay? That's the entire recursive algorithm. See, it's recursive, traversal, 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 calls traversal twice, right? What is the running time of this algorithm? Well, look what it's doing and figure it out. We get to the root nodes 6, we say visit the left side. Visit the left side. Visit the left side. Visit, oops, there is no left side, right? Now print this node out and visit the right side. There is no right side. Back up to the previous node, right? That's what a recursive call is doing, right? Now, print this node out. Go to the right side. Is there anything further down? No. Print the node back. Anything on the right side? No. Back up. I'm finished here. Back up. Print this one out. Go down to here. Print this out. Back up. Back up to here. Print this out. Go down to here. Print this out. Back up. Does everybody agree that's what happens on an in-order traversal? How much time did that take? Okay? If we think about it, let's count what we did. How many nodes are there in an n-node tree? N. Okay, that's not hard. How many edges are there in an n-node tree? That's a little bit harder. N-ish. Okay, n minus 1 is the right answer, but to my mind it's n, right? How many times am I walking over each edge? After each edge, how many times am I walking over each edge? Twice. Does everybody see that? So the total number of steps here is really going to be n steps for printing, once for going down to each node, and once for coming up from each node. So that tells me that there's a total of n plus n plus n equals n things happening. How many people are with me here? Notice the shape of the tree did not matter on the time complexity of an in-order traversal. If you want to do an in-order traversal of a list, how much time does it take to walk through a sorted linked list? N steps, right? The balance doesn't help you here, right? Okay, so but what the important thing here is that it takes linear time to do an in-order traversal. How many people see why it's linear? How many people don't that have questions? I know people don't. How many people don't that have questions? Okay, any questions? Okay? So if so, what is the complexity of this thing? How would we now, what is the complexity of now, how would we use insert and in-order traversal to sort? What would be the way we would do it? What's the first thing to do? What's the first thing we do? Insert, I mean build the tree is the way I would say it, right? So you start out 4, I equals 1 to n. Insert into tree T, a sub I, right? And then do an in-order traversal, starting from the root of tree, the root of T. Okay? What's the cost of building the tree? N log n. What's the cost of doing the traversal? N. What's the cost of the total algorithm? N log n. Does everybody see that? So we've got 3 n log n algorithms. Which one of these is better? Okay. To my level of resolution, they are the exact same thing. They are all n log n algorithms, right? And at that level of my understanding, I cannot choose between them. Okay, I am perfectly happy I've got an n log n algorithm for sorting. If I've got 3 of them, I guess that's even better. Okay, any questions here? But the important thing here is to see how you use the balanced binary search tree as a tool to build a more complicated algorithm from. Okay, and somehow all the complexity of sorting, you invented 3 n log n sorting algorithms once you have the power of the balanced binary search tree. Any questions about that? And that is the way that I, as an algorithm designer, think about balanced binary search trees. Any questions? Okay, any other questions about trees before I move on a little bit? Okay, any questions? Okay. So what I'd like to spend this class talking about is talking about another implementation of dictionaries called hashing, basically hash tables. And what I want you to do is to mentally, first of all, there was this thing, I think it was F. Scott Fitzgerald said, that the sign of a first-rate mind is the ability to keep two opposing ideas in your mind at the same time. Okay? I'm going to assume you guys have first-rate minds. So we'll talk about two different opposing ideas in here. The first is the idea of worst-case analysis. We are very interested in this class in the big O worst-case analysis. Okay? And that's what's driving most of what we're going to be doing here. Okay? On the other hand, we're also interested in useful tricks and practical things that might not have as great guarantees in some sense, but are still useful for algorithm design. And hashing is one of these things that doesn't offer you guarantees. Okay, and so from a big O sense, I would hold my nose up and not talk about hashing. On the other hand, it is a very practical technique, and it would be remiss of me to not explain this to people. Okay? So keep these two things in mind. Big O sense, hash tables are bad. If you try to sneak a hash table into one of the exam questions, when I tell you about give me a big O n log n algorithm for this, you sneak a hash table in, I go shoom shoom, because I'm looking for worst case analysis. Okay? But for practical things, it's important to know about hash tables, and that's why I'm going to talk about it here. Any questions about the distinction that I'm making here? Any questions? Okay, so let's look at what a hash table is. Okay? A hash table is an idea is going to be a way of maintaining a dictionary that exploits the fundamental property of an array. Okay? An array is a wonderful thing because if I know the index of what contains my value, I can retrieve it in constant time. Does everybody agree with that? How much time does it take to find the 963,436th element of an array? O of 1 time, just constant time, right? So what we're going to do with a hash table is an idea that we're going to try to reduce the problem of searching for a key, a name like Skeena, to a problem of looking it up in an array. If we could reduce it to a problem of looking it up in an array, that would be constant time. And so I need a way to somehow take the search string that I'm looking for, let's say Skeena, and converting it to an index of an array, which means converting it to a number. An integer. Does everybody see that? So the key that's going to make a hash table work is something that we call a hash function. And a hash function is a mathematical function that maps the keys of whatever you're interested in. Okay? In the case of maintaining a class roster, it is names. Okay? To integers, so we can use them as indices in an array. Any questions about that? I will show you examples of this. But that is the big philosophy here that we want to do. We want to make search look like array lookup. Okay? Bunk, come to me. So what we're going to, in fact, let me come back to this collision issue. Okay, let's talk a little bit more about these hash functions. Okay? What we need to talk about now is how can we take a, a key, okay, a string like Skeena, okay, and map that to an integer. Okay? So how can we take a text string, okay, Skiena, and map that to a number, okay? Well, the simplest way to do it, okay, would be to interpret the text string as a base, whatever the alphabet size is, number, okay? You guys are used to base 10 numbers, right? What was a base 10 number? 1, 3, 2. Why is it, if this is a base 10 number, what does this mean? That's 2 times 1, right? Plus 3 times 10, plus 1 times 10 squared. Does everybody see that? That is a base 10 number. What is a base 128 number? The lower digit is going to be a number between 0 and 127, right? Just like in a base 10 number, the lower digit is a number from 0 to 9, right? The last position we multiply by 1. The second symbol is going to be a base, a number from a digit which has a number value from 0 to 127. What are we going to multiply that by? 128. The third digit we're going to multiply by what? 128 squared. Does everybody see that? The next one is 128 cubed. Fourth, fifth. Okay? If, in fact, the printable ASCII characters, the characters that you build text strings from, there's only 128 of them, then any text string that you have in here can be interpreted as a base 128 number. Okay? Any questions about that? How many people see this? How many people don't see it? This is a good. If you don't see it, this is an important thing to see. Here I have done this. Note that if I want to convert a text string to a big integer, okay, an integer, I can, if my character set is 128 characters, by interpreting, taking every letter, the ith letter of my string, converting it to a character number between 0 and 127, my text string here is equivalent to exactly one number written in base 128, which of course is just an integer in any base. Any questions about that? Do people see how I have taken my integer, my text string, and I have converted it into a number? Any questions? Yes?
So like a strong one-way cryptographic hash function like MD5 or SHA-1 isn't good in this sense?
Okay, so let's talk about cryptographic hash functions at the end of class. Okay, so there's interesting, but that's a little distraction at the moment. Okay? Any questions? Okay? All of them are taking a text string, even those things. They're taking a text string or a bit data and munching on it to produce a number. That's what those functions are doing. That's what my function is doing. Okay? Any questions about it? Can anybody come up with another function that could have converted the characters, okay, the text string into a number? Can anybody come up with another function for that? Yeah?
Well, I could give a perverse example and convert all strings to 0.
So you could have a hash function that takes every string and maps it to 0. Okay? That is certainly true. Now notice a couple things about it. One, of course, is that there's no information about the string in the number, right? So it will be a very perverse thing. Can anybody do a better job of converting a string to a number? Yeah.
Slightly better would be using the length.
One possibility is to use the length, right? Skeena, it goes to 6, okay? And, Bush would go to 4, right? Now, what we would like to do, though, if we think about these are ways of taking names and mapping to numbers, okay? We want these hash functions to have two properties to them. One is that they're cheap to evaluate, meaning something like linear in the size of the string, right? Certainly converting it to 0 is cheap, right? 0, okay? But we also want it to use scattered numbers in a wide way, in an even way, okay? And why is that? Well, let's first think about it. Suppose we just use this as a hash function, okay? Well, we use the function I defined. Now, if we want to build a table, an array to store people according to the numbers I'm getting from this function, how big must my array be? Too big, extremely big. Does everybody see that Skeena here is being mapped to a very, very big number, right? I mean, S is going to be something like 36 times 10 to the 120 to the fifth, right? What's good about this is it's mapped to a unique number. That's better than the 0. That's better than the length, okay? The trouble is, this is right now an arbitrarily unbounded problem. And if I want to use this as an array index, I've got problems, because I've got to allocate an array big enough that 10 to the gazillion is an index in my array. Do people see what the problem is? I want to allocate an array big enough for a hash table. If I'm going to store 1,000 things, I want to have an array of size 2,000, something like that. Okay? So I need to do something else to this big function, integer, to make it smaller, so that I will use, if I decide my hash table is of size m, it will scatter it evenly. Yes? So what is the way that I can take this big number and map it to a smaller number? Okay? The magic idea is to take that value and take it mod m. What does the mod function do? It is the remainder. That's the remainder function, right? So suppose, let's say, I had a huge, huge number, okay? And I want to map it to a number. Let's say I have a small hash table of size m. I have to somehow map this big thing to a small thing. One possibility is I divide it by m and I take the remainder. And the remainder, when I divide it by m, is going to be a number between 0 and m minus 1. Any questions about that? Does everybody see that that has the property, okay, of taking a big number and mapping it down? Okay? What's more, it tends to map it down in a way that will use all the numbers from 0 to m minus 1 in a fairly uniform way. What is the theory of this? It is the same theory as a roulette wheel. Have any of you been to a casino and seen a roulette wheel? It's for gambling, right? And a roulette wheel is a way of generating random numbers for you to bet on, right? How does the roulette wheel work? The guy who's running this thing takes a ball and throws this ball on the outside of the roulette wheel, where it spins around and around and around, right? Around and around and around, and you're betting on it. Bet your thing, and the ball starts slowing down and starts slowing down. Then it goes ka-chunk, ka-chunk, ka-chunk into a cell, and you lose, right? What is happening here in a roulette wheel? Roulette wheels pick random numbers, right? They're hard to predict the outcome. If they were easy to predict the outcome, casinos would be out of business, right? What is it doing? It is taking the long roll path of the ball is a big number. Does everybody see it? If we unwrap the long path, ultimately settling it into one of 36 slots is taking the remainder of that path, the length of that path, mod 36. Okay? And that kind of an argument works in a roulette wheel to use all the slots equally. Any questions about that? And so that is sort of the theory or the vision of what we want our hash function to do. We take your name, build a huge number from it, okay? Then we take the mod function to cut it down to size in a way that it should use any one of the values from 0 to m minus 1 equally likely, okay, or something like equally likely. Any questions about that? Is it now clear how we can go from a, from a name, like Skeena, to a number between 0 and m that we can now use as an index in an m-element table to store Skeena at. Any questions about that? How many people are still with me? Okay, good. Okay? Now, again, when you study the theory of hash functions, there's actually are certain details that come up in how you should design your hash function, how big m should be, and stuff like that, that gets into some very interesting number theoretic things and stuff like that. I don't want to really go into that. So there's a certain amount of science that should go into these things. But in principle, if you take the big number, mod m, you get numbers scattered, hopefully, uniformly between 0 and m. Any questions? Okay, good. So what are we going to do with this? Now, to complete the idea of a hash table, okay, we have a way of taking all the people. Let's say we want to build a data structure to represent all the people in this class, okay? We will convert each of you into a number between 0 and m. This might be m minus 3. It might be 17. This might be 36. Whatever it is. I can take every one of your names, convert it to a number between 0 and m minus 1. Okay? Then I will store you at that location in the array. The problem comes that it could very well be that when we hash it, Skeena and Obama might actually get hashed to exactly the same spot. Okay? And if so, what would that mean? If Obama was in this class and Skeena was in this class, okay, then there would be one spot in the array where we are expecting both Obama and Skeena. Does everybody see that as soon as we make the decision to shrink the array, to take the mod of that unique number, now there is going to be collisions. Two different names can come to the same spot in the array. Okay? And so we need some mechanism to deal with that. The conceptually simplest thing to do is to have at each spot in the array be a linked list. So if Skeena and Obama both got hashed to element 6, here we have a bucket of all the names that got hashed to 6. This would be Skeena, and after me comes Obama. Okay? Any questions about that? The important thing is that with this in mind, now you should see I have a data structure that is capable of correctly doing insert, delete, and search, okay, for keys. If a new element comes along, let's say we want to have, who would we like to have join the class? Okay? Gingrich. Well, okay, Gingrich. Let's just say Gingrich now. If Gingrich wants to join the class, what are we going to do? We're going to hash Gingrich. He's going to get into an integer, right? He's going to be at the end of the class, actually. Okay? But if his hash code came to 11, we will add him to the end of this data structure, right? He will be in the linked list indexed from 11. If we now want to delete, Obama decides he can't take this course for credit. What's going to happen? To deal with Obama, we're going to take Obama's name, compute the hash function on it. It's going to tell me that he has to be in bucket 6 if he's in the class. That means he's going to be in this spot. I will search this linked list till I find Obama, and then it is like linked list deletion, right? Any questions about it? So the problem with two people getting the same hash code is simply that that list is going to get longer than what I would like. For efficiency, I would like that list to each be of size 1, okay? But if that list is generally short, this would give me a constant time solution to my problem. Why? Suppose, let's say, I have a hash table with n buckets. Suppose I am going to insert n keys in it. on average, how many keys will be in each bucket? N buckets, N keys, there will be 1. What if I set my hash code to be of size 2n? Still linear in size. And I put n things in it. What's the average number of elements in a bucket? 1/2 of an element, right? In general, the linked lists, when I get to them, if I did a good job scattering my keys around, are going to be short, ideally constant size. And therefore, this will give me a constant time dictionary operation. In constant time, take the constant length string Obama and convert it to a number. Divide that number mod the size of my hash table in constant time. Go to that array location in constant time. And then scan through a list that hopefully has no more than 1 or 2 elements in it. If so, that takes constant time. And the whole search insert operation will take order 1 time. Any questions about that? How many people see why this works? Gets the basic vision of how the scheme works. Any questions here? Any questions about how a hash table works? Okay. So this is in principle a wonderful thing. But its wonderfulness depends upon having a good hash function. This gentleman proposed a hash function where he mapped everything to 0. What would have happened if we employed his hash function? Okay? Every element would have gone into this linked list, right? And then when you say Obama, he's in bucket 0. Skeena, 0. Gingrich, 0. Okay? Your problem has reduced to searching in a linked list of length n. How much time does that take? Order n. So the worst case here is very ugly. But if you have a good enough hash function, and if you are not perversely unlucky, okay, you can store a dictionary in linear space that should give you constant time access. On average, expected usually, cross your fingers, okay, for insert, delete, and search. Any questions about that? Yes? So how does this deal with different words in the same letter? That's an interesting question. So let's think about what are 2 words that have the same, that have the letters in the same order? That are same letters, different order. Anyone think of 2? Okay. Rat and tab, I think I'm coming up with, right? Rat and tar. That looks like one. Right? Does everybody agree? Okay. So let's look at what would have been what would my hash function do? My hash function would have taken rat and multiplied the t by 1, the a times 128, and the r times 128 squared. Does everybody see that? This would have multiplied it by 1, by 128, and by 128 squared. Does everybody see what is good about this function? Is that even though they have the exact same letters, rat and tar are likely going to the same place, different places, right? I say likely because when I take mod to size m, they might still collide. But does everybody see that the reason I did this exponential thingy, where I treated it as the sum of, as a base 128 number, the reason I did that was for just this reason. If I had had a different hash function, which would have just added the digits together, does everybody agree that if I added the digits, multiplying it by 1 instead of this 128 to the something, these 2 words would have gotten to the same hash value, okay? And that would have been bad. That's why my hash function is good. The other hash function would have been less good. Any questions about it? Okay? So selecting a good hash function is the key to making hash tables work right. Again, let me give you just an example again. Sometimes hash functions are good and sometimes they're bad. And just on an intuitive level. Okay, let's take a look at it. Everybody in here has a social security number. Suppose I hashed you to the first 3 digits of your social security number. Okay? Let's think at how good a hash function that is. Okay? So think about your first 3 digits of your social security number and tell me. What is it? 068. Okay, so I'm going to put this person in here. What's yours? What's yours? What's yours? 099. Okay, what's yours? 107. What's yours? No. 102. 111. See how well we're using the whole hash table? 110. What about yours? 118. See how smoothly we're using all the hash table? Okay. We're not using all the hash table. Does everybody see that? Does anybody know why? Yeah?
Because we were all born around the same time.
You were all born around the same time in about the same place. You were all born in New York at roughly, comparable times. Okay? And the way they assign Social Security numbers, the first few digits, the first 5 digits are fixed by that. Okay? The last 4 digits are assigned essentially randomly or sequentially within a region. Let's now look at the last 3 digits of your Social Security number. Okay? Now let's see what we've got. You still don't have one. Oh, no, what's yours? What? 623. 623. Does everybody see it? No, no, no. 450. Yeah? Last 3. 256. Yeah? Somebody else. What? 837. Does everybody get my basic point here? Does everybody see already that the last 3 digits of your Social Security number function as a much better hash value than the first few digits? Does everybody see that? And so when you have a hash function, you want a hash function that will scatter things around randomly, nicely around the table. If so, you get good performance. If you do something silly, and it's very easy to do something silly, where your hash function does not scatter things around uniformly, you get bad performance. Any questions about that? Okay? Yes? So the question is, you have to test your hash function. So it is clear that there is a certain amount of skill that has to go into designing a hash function. Okay? And these days, and so again, if you read books about hashing and stuff like that, there's a lot of theory behind to try to choose hash functions right and stuff like that, to try to minimize these kinds of problems. Now, fortunately, you guys live in a world where you program in languages like Java. Okay, and you guys are not afraid of hashing. Why are you guys not afraid of hash tables and hashing? Because it's all built in, right? Somebody else built the hash function. Okay, hopefully Mr. Java did a good job with it, right? But internally, this is what is going on with a hash function. Okay, and it should be clear that if you have a good hash function, and you leave enough room in your hash table so that you have a lot of buckets, okay, this should work out okay. There's no guarantees, so in a big O sense, we can't use this, okay? But if you're lucky about it, or you're not unlucky, good things are going to happen. Any questions about that? Okay? So what is the performance of a hash table? If you use chaining, which is the method that I have talked about, where you use linked lists to resolve collisions, or if you use some more complicated, some method where you look to see if if there's another element in the spot, and if so, maybe look for the first open hole or something like that. Treat it as an array and not as an array of linked lists. Okay? In either case, if you have enough memory in it and stuff like that, search, insert, and delete in expectation is constant. In the worst case is linear. Okay? How would we find, let's say we have our regular hash table. We have a hash table with m buckets and n elements. How do we find what the minimum element in the hash table is? Let's think about it. We have these other dictionary operations as well. How do you find the first person in alphabetical order in the class? If I represent the class by a hash table, what would I have to do to find that person? Yeah?
You have to go through every one because if you're plotting all of the hash codes, put it into the table, you don't know.
What it's saying is that the minimum person is in a bucket. Which bucket are they in? I have no idea. So I have to check every bucket. And then I have to cruise through every element of every list in the bucket. Every element in the list associated with every bucket. There are a total of n elements. There are a total of m buckets. There's a total of n plus m time. Yes?
Assuming you made the hash table yourself, isn't there some kind of way you could abuse the system you made to get yourself to the right bucket?
So you're saying, is there any way I could have done something fancy here to try to know which bucket has the min? And the answer is, if I am doing a good job with a hash bucket, hashing, why do they call it hashing? Okay, what does the word hash come from? It's supposed to come from my corned beef hash, making a mix of something. My hash table is good if my elements are scattered around. Okay? What is the minimum number? What can I say about the minimum element in the class? What property does the minimum element in the class have? It has to do with the fact that it's less than anybody else in the class. It's not anything intrinsic in that element. Does everybody see it? If we were teaching a course about how people whose names begin with Z are the best people in the world, who's going to be first in alphabetical order in this class? Zabrinsky. Okay, does everybody see that? That would be the minimum element. So there's no way you can decide, well, I'm going to put this guy in without, you don't know anything about what bucket the min is, or the max is. Or if you have an element, you don't know where its predecessor or successor is. If you have a good hash function, two keys that are very, very similar will be put in different buckets. Okay, wildly different buckets. You don't generally want the property that similar looking keys get tossed into the same bucket. Can anybody think of why that is? Why don't you want similar keys to get tossed in the same bucket? Yes?
Because
Comparing
comparing keys might be expensive.
keys might be expensive. I'm not sure quite how to interpret that. Yeah?
If they're similar and you use it for something along the lines of passwords, then a wrong password would be similar to close.
Well, okay. What I'm going to say is, if my keys that I'm asking for all have very similar names, they're all going to get tossed in the same bucket. If I, let's say, had a property, well, let's say I took the beginning of your name and I hashed people into buckets based on the first few characters of their name. How many people in this room are Korean? Raise your hands. Okay, you don't have to. But what's the most popular name in Korea? Kim. And what fraction of Koreans are Koreans are Kims? Something like 15%, 15%. If we hashed Koreans into a hash table based on the first beginning of their name, so we kept similar names together, what would happen? The Kim bucket would be stuffed, right? And that's exactly what we don't want in a hash function. Does everybody see that? So to do what we want with a hash function, we want similar names tossed in different buckets, okay? And my hash function would tend to do that, okay? Any questions about that? Okay? So pragmatically, hash functions are very good things, okay? Usually, the expected behavior works if you do a good job building your hash function. In the worst case, you are in trouble. So when we use dictionary data structures For algorithm design, we assume the bounds from balanced binary search trees. So you're allowed in any algorithm design problem in this class to use a balanced binary search tree as a dictionary. And say any one of these things can be done in log n time. You can't pull any fast one using hashing. Any questions? Because we're talking about worst case analysis. Okay, any questions about that? Okay. Well, let's go on a little bit more. This is something I want to show you a little something about why hashing is a clever thing. Okay, so you now know about hash tables. Any questions about hash tables? You should all now know about why hash tables are a good thing. Okay, and as a data structure, how they work. I think you now should know it. If someone locked you in a room, you should be able to implement at least a rudimentary hash table pretty easily. Now, hashing is an important idea and technique that goes beyond just building hash tables. Okay? It can be used to solve a lot of other problems. A very good algorithms book, not as good as mine, but a very good one, was written by a guy named Udi Manber, who used to be the chief scientist at Yahoo. Now he's a big mucky muck at Google. And at one point he went to give a talk to all the algorithms people. What were the important algorithms that you need to know at a company like Yahoo? He said the three most important algorithms were hashing, hashing, and hashing. Okay? There are a lot of things you can do with hashing if you're clever about it. Okay? So let's take a look at some of these, okay, just to give you a flavor for why hashing is important beyond hash tables. They're good for hash tables, but there's other ways to think about it. So let's think about this problem of, in Google, the search engine, it crawls the web, it finds another page, okay? To stick it, before it sticks another page in an index, it wants to make sure that page isn't in the index before. Does that kind of make sense? Has anybody ever seen a world where the content on one web page is replicated on another web page? People have seen that, right? There's a zillion copies of every Wikipedia page out there, right? So how is it that Google can tell whether or not a Wikipedia page it has scanned is somewhere within its database or not? If you think about it, the web has several billion documents on it. I download Skeena's homepage. Is Skeena's homepage anywhere else on the web? I could compare it one by one to every one of a billion other documents, but that is slow. What instead can I do? Using hashing, what can I do? Any ideas? Yeah?
Well, if you compute the hash code of your page, then all you need to do is compare it with all the other pages that have received the same hash code.
So the important point, what I'm going to do is, Udi here, he knows how to hash, okay? He will have taken every one of the web pages that Google has already scanned and computed its hash code. A web page is a big thing, right? A hash code is an integer. It can be relatively small, 128 bits, 256 bits if you want, right? And now it builds a data structure of basically the hash codes, right? It is very unlikely, if Skeena's page is twice on the web, when we hash it, the hash codes will be identical. Does everybody agree with that? And they will get hashed to the same bucket, okay? It is unlikely, if I have a big enough hash range, 256 bits, let's say, it is unlikely any one of only a billion other pages gets hashed to that thing. Does everybody see that? So if I want to tell if Skeena's page is really duplicated, okay, I can now look at the small number of documents with that same hash code, right? Or if I'm Google, I probably don't really care if Skeena's page is really there. I may say, is there somebody's page with this hash code? If so, that's probably Skeena's, another copy of Skeena's page. Maybe I'll throw Skeena's page out without even looking at it. If the hash code is big enough it is unlikely there will be collisions. The number of such collisions should be rare enough that I don't get too hyper about it, okay, if I throw something out by mistake. Any questions about that? Does everybody see that now instead of taking order 1 billion time to find if Skena's page is in there, it is now constant time, okay? Any questions about that? How many people see the scheme? Okay, very good. That's an important use of hashing. What's another important use of hashing gets back to what he was mumbling about earlier, about cryptographic hashing. Sometimes you have a world where you would like to, let's say, represent that a file, you'd like to be able to convince me that a file is not going to change without showing me this file. Okay? So let me tell you an example of a time when I was doing it. Okay? I was once involved as an expert witness in a court case. And one side's software, proprietary software, was in a directory that they didn't want the other side to have. Okay? But they were willing to let an expert come by and take a look at the files for one day. Okay? To prove that there was nothing bad in these files, right? And then the expert wanted to make sure that we weren't going to change anything. So how did he do it? He took all the files that we had, treated them as one big tar file or something like that, and computed a hash code of that file, right? Now he knew that he had the hash code, which was, let's say, 256 bits, okay? That was the hash code of these files. He's not going to get access to these files again, right? I don't want to give him the files. But I let him have the hash code. Now, what happens if I go in there and change one character in one of these files? What is going to happen to the hash code of these files? It's going to be different, right? So suppose I go in there and I sneak and I want to delete Skena's name because it really shouldn't have been in there, right? He comes back and he computes the hash code again, and it's going to be different, and he's going to say, aha, you changed that. Does everybody see this? He is able to, only with the hash code here, okay, I can't make a minor change to this and keep the hash code the same. Yes? Okay, so a lot of things going on here I don't completely understand. But what do I understand? Okay? We agree that virus companies are doing this sort of thing, right? You take your antivirus companies, right? You would like to find what is this file a virus? Well, if I compute the hash code of of this file, okay, and it matches a hash code in my database of hash codes of viruses, I have a quick way to tell whether it's a virus. That's one thing that he's saying. For this to work, it's got to be, or if he wants to see, another question is, if I put a virus in a file, how do I know that how am I going to detect that? That's what happens with viruses. They sort of slither into a file, right? If I take the hash code of the file, with the virus, the hash code is going to be different than without the virus in it. Does everybody see that? So that's the scheme, how you're going to use hash codes to detect viruses. Now he's saying, just to be the third thing he's saying, is, but what if I am very, very clever about designing my virus so the thing that it replaces doesn't change the hash code? That's really the tricky thing that he's got to be able to do. Right? And if I design my hash code right, a so-called cryptographic hash, it is hard for me to design a file with the hash code that I want it to have. I know I want to have this file have my virus and also have a hash code equal to that. If you have a sufficiently clever hash function, that is hard to construct. Okay? That's why they call it a cryptographic hash function. Okay? Question?
So if I know the key for prime number of the hash function, then I can do that.
You know, what you can do to invert a hash function, this gets into things like cryptography. This is now where the details of how secure is a hash and how do you break it and stuff like that gets into cryptography type things, right? But the principle here should be pretty clear. The hash code is a concise summary of the file, okay? By comparing the hash codes, I largely compare the files, okay, efficiently, okay? And if it is hard for me to construct a specific hash code to get a file to hash to something, then I get a certain level of security. Any questions about it? So, hashing, and hashing, important things. Think about it, but starting next time, we're back to worst case analysis. Thanks for your attention. See you guys next time.